Hello, my name is Özgür Burak Aslan. I will be talking about strain tuning of the excitons of monolayer tungsten diselenide. It is very important to understand the physics of the excitons as they dominate the optical spectra of transition metal dichalcogenides. And tuning the excitons are of crucial importance not only for applications in optoelectronics but also for fundamental studies. People have used various methods to tune the excitonic structure of transition metal dichalcogenides. They have used electrical gating by changing the doping level in the material, the binding energy, as well as the oscillator strength of the excitons have been modified. And the other way is dielectric screening. The excitons are sensitive to the nearby environment, so people have used nearby graphene layers to tune the excitons in monolayer tungsten disulfide. And the other method is to apply a magnetic field. All of these methods have been used to tune the excitonic structure, but they have been helpful for understanding the fundamental physics of the excitons. And people have observed a shift of up to 30 mV in the optical gap, the ground state exciton, and they have been able to tune the binding energy by up to 100 mV. So therefore all of these methods have been means of probing the excitons as well as tuning them. Now what about mechanical strain? We know that these materials are very strong. They can endure high strain up to 6 to 11%, similar to graphene. And strain have been used to engineer the band gap as well as achieving indirect to direct gap transition in ultra-thin TMDs. For instance, bilayer tungsten diselenide at 0% is an indirect gap semiconductor. At around 1.5% it is a direct gap semiconductor similar to a monolayer tungsten diselenide. So therefore it is important to be able to use mechanical strain for flexible optoelectronics and to figure out how strain affects quasi-particle gap, indirect gap, the binding energy of the excitons as well as their line width. But what about using strain to probe the excitonic structure? What about probing it as well as tuning it? So this is how we apply strain to the monolayer materials. We place them on a flexible substrate which is placed at the back of an optical stage, and upon bending the substrate we can transfer the strain to the monolayer, and then we probe our excitonic structure. So we have used photoluminescence measurements as we increase the strain on the material, and we observe a common redshift which was about 100 mV at 2.1% strain, and this shift is more than twice the line width of the A exciton, the ground state exciton. And we have confirmed the same results by performing absorption measurements. And we realized that the excited states of the A exciton are more pronounced. This was very interesting. And we have seen that all of the peaks that we observe become narrower with higher amplitudes. And this is very interesting, why this would happen by applying mechanical strain. Now let's look at this line width more carefully. So by looking at the PL spectra, we see that the amplitudes go up, but the total integrated areas do not change much. So therefore the line width must be decreasing significantly. This is more pronounced in the absorption spectra. So if we look at the A exciton line width, it is 42 mV at 0% strain, but it becomes 24 mV when strained. This is a significant drop, and all we did was to stretch the material. There is no temperature change, nothing, yet the line width decreases so much. And if you simply look at the images of a standard tungsten diselenide and compare it to the strained tungsten diselenide, it's impossible to notice any difference, yet they have so different optical properties. Now it is always good to compare tungsten diselenite to a sister material to see how the strain will affect its line width. Our tungsten diselenite result, and if you look at the tungsten disulfide for the same measurements, you see that the line width is already good at 0% strain, which is 30 mV, and it becomes 24 mV. It reaches the same value of 24 mV at high strain. And if you look at the spectra in between, the behaviors are so different for tungsten diselenite and tungsten disulfide. Tungsten diselenite starts with a much higher number and saturates at only high strain to the 24 mV, yet tungsten disulfide is already good and the line saturates very quickly and is nearly constant. And why are they so different? Okay, so this is a little confusing, and we need to understand first how the excitonic line width happens. Why do we have a line width at all? Then we can understand the strain dependencies better. Looking at the band structure of these TMDCs, we first see that there's a direct gap at the K point, and there's a nearby indirect gap, which is the KQ state. So KK versus KQ. And let's remember that the A exciton is a KK transition. The first broadening mechanism is the radiator broadening. Next, we have exciton phonoscattering, the first one being KK intravalley scattering. And then we have the intervalley exciton phonoscattering, so going from the direct transition to the indirect transition. So instead of having a sharp line width, we have this broadening line width of the A exciton. Now let's look at the strain dependence of the line width. Now remember that tungsten disulfide and selenite have very similar material properties, and these properties depend on the strain in a similar fashion. And these parameters are being mass, the exciton mass, the material density, phonon frequency, etc. Yet we have so different results from these two materials. Okay, let's look at the strain dependence of the line width. First, the radiator broadening, which is only a few millieV, and it doesn't change much with strain. It increases only a little bit. So therefore, this does not explain the difference between the two materials, and it does not explain the decrease in the line width. Next, we look at the exciton phonoscattering. The first mechanism is the intravalley KK scattering, and that also does not strongly depend on strain, and it does not explain the results. Therefore, we next look at the intervalley exciton phonoscattering, going from the direct transition to the indirect transition. Apparently, the theory predicts that as we increase the strain, the energy difference between the direct transition and the direct transition increases. So this is what happens. Once again, the theory predicts that as we apply strain, the energy difference between the direct gap and the indirect gap increases. Therefore, the scattering rate from the direct transition to the indirect transition will decrease, because we will need higher energy phonons, and we are less likely to find them as this energy difference between the direct transition and the indirect transition increases. So if we calculate that, we see that the difference between the two materials can be explained, and the significant decrease in the line width of these two materials can be explained. So therefore, we understand that tungsten disulfide was a more direct gap material than tungsten diselenite. So for tungsten disulfide and tungsten diselenite, we calculate the strain dependence of the KQ minus KK energy difference, and we realize that if we shift the tungsten disulfide data points by 60 mV, we can mesh the two data sets very well. So basically, it means that the indirect minus direct gap separation for tungsten disulfide is 60 mV larger than tungsten diselenite at 0% strain. So once again, tungsten disulfide is a more direct gap material than tungsten diselenite by 60 mV. That is why it already has a good line width. So there is less chances of exciton phonoscattering from the direct valley to the indirect valley, and increasing the strain does not significantly reduce the exciton phonon scattering because it is already a smaller portion of the total line width. But tungsten diselenite is a more indirect gap material, so the direct gap is closer to the indirect gap, so exciton phonon scattering is quite likely. And as we increase the strain, the total line width is very sensitive, and it decreases significantly as this energy difference is increased significantly. So to summarize the effect of strain on tungsten diselenite, we have achieved 2.1% strain, and we have reduced the optical gap by 100 mV, which is more than twice the line width. But let us remember that the line width of the band edge exciton was also tuned and decreased by applying strain, such that for tungsten diselenite it goes from 42 to 24 mV, and for tungsten disulfide it is from 30 to 24 mV, and we have attributed these to the decreased intervalley exciton phonon scattering rate with this mechanism. And we have seen that we have found good indication that monolayer tungsten diselenite and tungsten disulfide are already direct gap semiconductors at 0% strain. We don't have direct evidence, but our results are a strong indication of this picture. And such that these materials have different direct to indirect gap separations. So tungsten disulfide is more direct than tungsten diselenite, our results indicates. Therefore, we have established strain as a means of not only tuning the 2D materials, but a nice way of probing the 2D materials. Thank you.